And as usual, the tension is mounting.
8.9.
8.9? How'd you get 8.9?
62.5 divided by 7.
Yes, it's distance divided by time, so my average speed, no vector symbol over it, is equal to 62.5 meters divided by 7 seconds, 8.9 meters per second. And by the way, if this were a test, and we use 62.5 in order to get this right here, if you miss this one, and then use whatever this number is, the wrong number in this one, you could still get full credit for this, even though you missed this one. All right, questions before we do another one of these? Woo! Gary.
I'm confused. I'm still confused on how you found the distance the car traveled.
The distance traveled?
Yes.
All right. Can you picture that the car is traveling to the right and then comes back?
Yes.
All right. So if it's traveling to the right and then it comes back, the distance traveled would be basically what the odometer would read. It's from here to here and then to here.
Mm-hmm.
Whereas displacement only cares about, all right, there's my starting point, where am I relative to that? So were you okay with the 40 meters of how we knew it went?
No, I didn't. I couldn't understand how you got the 40 meters.
Okay, all right.
Yeah, I didn't understand at all.
So for the trip to the right, all I care about is for the first 4 seconds, what is that car doing? And the reason I say 4 seconds, because that's when it stops.
Okay.
So the first 4 seconds, it's traveling to the right. And I know it starts at 20 meters per second, and it goes to 0 meters per second.
Mm-hmm.
So my average is 10 meters per second.
Okay.
Regardless of how much time it took, average. If acceleration is constant, average is just the average of the first and the last one. Now we bring time into it. If he's traveling on average 10 meters per second for 4 seconds, how far does he travel?
Okay.
That's where the 40 comes from.
Okay.
And I know that from here to here is 17.5, that's what we found already. And then by subtraction, this piece right here must be 22 and a half.
Gotcha.
Okay. Other questions? So let's change the problem around. We're all pretty much the same there. Let's do another. Yeah, let's go with that one. So let's make that negative 20. And positive 8, and make that 9 seconds. Well, at least we have on video that the board was mostly clean at one point. All right, so let's go ahead and do the table method, just to start out with. Time is in seconds, velocity in meters per second. Start out with just the absolutely stunning diagram. We'll make to the right positive, but car starts out going to the left. If the right is positive, then the car will go to the left. Problem will last for 9 seconds. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so what is the velocity when the problem starts?
-20.
Just trying to start getting into the habit of throwing the units in there also.
-20 meters per second.
All right, there we go. After 1 second, how fast is the car going?
Positive 8 meters per second.
Ooh,
Wrong, 7 seconds. 9 seconds. -12.
no.
Oh.
Oh, yes, -12.
That's what I got, but wouldn't you,
Yeah, the 8 is the difference.
okay.
So -12, so the change in velocity is -8. This would be meters per second. After 2 seconds, oh, that's, sorry, positive 8 is the change. After 2 seconds, 3. Let's run it down.
4 meters per second. 12. 20. 28. 36. 24. 52.
All right. Well, we answered the first question already. 52 meters per second. Or, for the algebra, that's equal to the change in velocity over change in time. So I have 8 is equal to my final velocity minus my initial, which is -20, divided by 9. Cross multiply, I have 72 is equal to VF plus 20. So VF is equal to 52 meters per second. Average velocity.
Is it 16? 16?
16?
Yeah.
Yes. 16 meters per second, because if you average the first and the last values, 52 plus -20 divided by 2, which is 32 divided by 2, which is 16. The most common mistake for people finding average velocity by averaging the first and last values is they add them up and then they divide by 9 or 10, based upon the number of seconds or number of numbers, as opposed to just the straight up, you're averaging 2 numbers. All right, displacement.
Is it 144 meters?
Quite possibly. Let's see. Yep, 144. How'd you get that?
I've done, the average velocity times the, time.
Right. So, 144?
Mhm.
Okay. 16 meters per second for 9 seconds. So average of 16 meters per second times 9. Right. Questions to hear? All right, at what time does the car stop? First off, it's somewhere between 2 and 3 seconds, because that's when we go from a negative to positive, or last time, you're looking for when you go from positive to negative, when the sign changes for velocity. And because of symmetry here, it would be smack dab in the middle, so 2.5 seconds. Or, for those algebraically minded, 8 is equal to 0 minus negative 20 divided by time. Same formula here, just we now know what the velocity is for when it stops, just trying to find time. So 8 is equal to 20 divided by time. Cross multiply that whole bit, and time is equal to 5. So it travels, this is at 0 seconds here. It travels for 2.5 seconds. It stops and then turns around, and at 9 seconds, it is, well, 144 meters from where it started. So if that's 0 meters there, this is 144 meters. It is a positive displacement, so we're on the plus side. So now to find the distance traveled, we need, again, we have to figure out how far does it go before it stops. What is this distance here? So for the first 2.5 seconds, what is the average velocity? All right, what's the initial velocity? At time 0, what's the velocity?
Negative 20.
Okay, when it stops, what's the velocity?
Here.
What's the average velocity from going from negative 20 meters per second to 0 meters per second?
Negative 10.
Yes? For this duration right here, from beginning to stopping, this is at 2.5 seconds. Negative 10 meters per second. So if the car is going on average negative 10 meters per second for 2.5 seconds, how far did it go?
Negative 25.
Thank you. So this is 25 meters negative if you want to consider direction. So the car goes 25 meters to the left, stops, 25 meters to get back to the starting point, and then ends up 144 meters from where it started. What's the total distance traveled?
194.
So what average did you use to get, 16? Or what average did you use
To get
to get,
to get the 25, or did you go back
Well,
further?
last time we used, 4 seconds as the average. What did you use this time, going down the table?
Oh, the car stops at 2.5 seconds. It stops halfway between here.
Alright.
And so the average is negative 10 meters per second for that 2.5 seconds.
Okay, gotcha.
So, okay. So we're starting here, we go to the left 25 meters, we stop, come back 25 meters, and we end up 144 meters, not to scale. Again, displacement cares about where are you relative to where you started. So the 25 left and 25 right over here is a wash, but the distance doesn't care about that. It cares about the actual distance, how far it's actually been traveled. So 25 plus 25 plus 144, and that's where the 194 comes from. And the car's average speed, .5 repeating. Second.
Is it 21.5?
I assume the 5 repeats. So 21.5 meters per second. Just distance divided by time, 194 meters in 9 seconds. So the average speed is about 45 miles an hour.
Is that just meters per second, not meters per second squared? For the speed?
It's meters per second. Speed and velocity have the same units. All right. Let's take a look at another set of problems where not all the information is necessarily given to you. You just have to know that some of the missing information. Let's see, who's still writing down? Any objection if I erase? Oh.
I'll be 194 or 144?
That's 194 there. It's 144 here.
Okay, and you got that by doing 25 minus 144?
So, for how I got this number?
Mhm.
Okay, starting here, goes to the left. We figured it went 25 meters to the left. Then it takes 25 meters to get back, so now it's traveled 50 meters. And then it ends up 144 to the right of where it started.
Okay.
So 25 plus 25 plus 144.
Okay.
That's where that comes from.
Would that be negative and stuff, or just?
If we're doing distance, they're all positive numbers and you add them up.
Okay.
If we're doing displacement, that's negative 25 plus 25 plus 144, which gets you 144.
Okay.
And Manal, I missed what you said?
I'm just understanding.
Okay. All right. Anything else before I erase? All right. Oh, just so we'll make it a car. A car is dropped from a helicopter. After 6 seconds. And then all those same questions. There are 2 pieces of information, and when I gave the problem before, I gave you 3 pieces of information in the problem itself. Now I've only explicitly given you 1 piece of information, that's the 6 seconds. But there are 2 other pieces of information that are implied in the language. I am going to make the assumption that since there is a car and a helicopter, that only exists on Earth. We are not in some foreign land. Or some, not foreign land, we're not in some strange world. So implied happens on Earth. So the two pieces of information that are not given explicitly in the problem, are the initial velocity and the acceleration. What is the initial velocity of the car? Yes. What's the key word that tells you that?
Drop.
Yes. If the initial velocity were not zero, then the word dropped should not be used. It would be thrown, tossed, something along those lines. Dropped implies it starts at rest. Acceleration. Pardon? No. If velocity is zero and acceleration is zero, that car's hovering. Which again, really cool effect, but no. This is why I said that takes place on Earth. If I said it took place on Mars or Jupiter or some other planet, then this number would be different, but it is relatively constant. It is not officially a constant, but it's relatively constant for a planet. The whole thing? There we go. If somebody said it already and I missed it, sorry about that. 9.8 meters per second squared. What is the direction of the acceleration? It's a vector, so it has a direction. Yes, down. So down. Let's just make down positive. Just make life simpler. So 6 seconds. So we start out with time in seconds, velocity in meters per second. We're going 0, 1, 2, 3, 4, 5, 6 seconds. So velocity is 0 to start with. What is the velocity after 1 second? After 2 seconds? Keep going.
29.4. 39.2. 49. 58.8.
So we have the final velocity now. It's going 58.8 meters per second. What is the car's average velocity? Yep. What is the displacement? Or how would you find it?
Average velocity times time.
Yes. So 29.4 times 6. What, 76.4? I think I saw a nod. What time is the car stopped?
At 0.
Yeah. Oh, that's meters right there. The distance the car travels. Yes. It's only traveling in one direction, so there's no turnaround. We don't have to be doubling back. And then average speed. Meters per second. Yeah. So this is an example where the speed is the magnitude of the velocity, just because it traveled in only one direction. I'm going to quickly zip through something right here. In this situation where we start at rest and we just let it drop, this 58.8, that's just the acceleration times time. That's all that is. So my average velocity is the average between 0 and whatever acceleration times time is. So that's 1/2 acceleration times time. So my displacement is my average velocity, so this is average velocity, is my average velocity times time. So this right here is 1/2 times acceleration times time, or 1/2 at squared. This is the formula that Hewitt gives you in chapter 2, the 1/2 at squared. Please recognize, in order to use this, acceleration is constant, and the initial velocity equals 0. You can only legitimately use this formula if it starts at rest. Or if you're looking at it right, if it ends at rest, but there must be rest at one end or the other.
And that's for the displacement.
Yes. So I think it's like the last formula that Hewitt gives you in chapter 3. Perhaps not the last one. In chapter 4, that's why. Yeah, he gives you this formula or something very similar to it on page 48 of the book. He also narrows it down. He puts one other restriction on it for free fall. This equation actually works even if it's not free fall, as long as acceleration is constant and initial velocity is 0. He does it specifically for free fall, and so the symbol he uses for acceleration is the lowercase g. So he has 1/2 gt squared. And g just means acceleration due to gravity. But I know I'm rushing that at the end. Hope you have, I'll see you Friday. I still hope you have a good weekend, but I'll see you Friday. Don't forget to print out the lab. Force table lab.
So in an instance where that wouldn't be free fall, to use that equation, would it work if you had like a ball and the initial velocity was 0 and then you like pushed it? Could you still use that?
If acceleration is constant, yes, you can.
Thank you.
Thank you.
Certainly, certainly.